Okay, ladies and gentlemen, let's continue with Chapter 7, External Forced Convection. Forced convection consists out of 3-4 chapters. We firstly did Chapter 6, which was an introductory type of chapter that just introduced convection heat transfer to us. And then after that follows the, let's call it the 3 more chapters which are more applied. The first one that we are busy with is Chapter 7, which is external forced convection. The next one, Chapter 8, internal forced convection. And then Chapter 9 will be natural convection. Right, so we are busy with external convection. So that is where we have convection heat transfer on the outside of bodies. And we've started with the most simple body, which is a flat plate. Okay. Then we're going to go over to another geometry, which is going to be cylinders and spheres, and then banks of cylinders and spheres. But very important is to remember that in terms of external forced convection, what is written in this chapter is not the body of knowledge in terms of everything that we know. There are lots more. Okay. But in this chapter, just some of the most important things are summarized for you. And if in industry you get other geometries, then you will have to go and look in literature to get that information. Okay. So before we continue, I want to ask you, please look up the Prandtl number for engine oil for me at a temperature of 20 degrees Celsius. You'll think this is a very simple thing to do, but there's a very, very important lesson in it for you, and a lesson which you will have to learn in many places in this textbook and also in many other textbooks. Okay, so engine oil at the temperature of 20 degrees Celsius. Not to waste time, it is on page 882. Page 882. Engine oil at a temperature of 20 degrees Celsius. You've got it. Okay. So, do you agree with me? The Prandtl number, look at the Prandtl number for me. Prandtl number is 10.863. Okay, hands up if you agree. Okay, I see there's 1 or 2. Very, very important is, please take note, it is a comma, so it is 10,863. Okay, so take note of it, it is very important. Then in terms of the problem that we did, example 7.1, in the previous lecture, it was over a flat plate, and in the textbook, it started with a case of, or it only looked at the laminar part of the flat plate. And for that, it was a very good selection in terms of oil being used, or something else, I can't remember. But in any case, with a very high Prandtl number. And one of you, which is very good, indicated to me, but this Prandtl number is too large. And you're right, I shouldn't have done it in this case. So the problem was a flat plate, and the problem in the textbook is only for the laminar part. Now in the laminar part it is fine, but then I actually wanted to look at this problem on a little bit more dimensions, and I said, well, let's make it longer, and let's start looking at the turbulent part also. Now the turbulent part, Prandtl number, the equations that we used, is valid up to Prandtl numbers of 60. Okay, so for the turbulent part of the equations, I didn't use the right equation. We should have actually used the equation of Churchill and Ozoe, which is also in your textbook. Okay, equation 726. Okay, so it would be more correct to do it for that, but I think if you go and redo it at home, when you work through it, rather select water. Okay, rather select water, because then it is in the Prandtl number range. Go and calculate how long it will take before the flow changes from laminar to turbulent, and make the plate about double the length and 1,000 times more. So do the same thing in principle that I did with the previous problem, but just use a Prandtl number which is in a range, typically that of water. Okay, so we've also started with the previous lecture at flow over cylinders and spheres, and we've looked at typically the characteristics of the CD value as a function of Reynolds number if we have flow over the cylinder. So there's the cylinder with a certain diameter, and typically what we would get, and you did that in fluid mechanics, is the characteristics of CD as a function of Reynolds number would do something like this, and this transition is approximately at 2 times 10 to the 5. Okay. Now the flow over a cylinder is geometrically a very, very simple geometry, almost one of the most simplest one that we can get, but the flow around it is very, very complicated. So if the Reynolds number is very, very slow, it would have a perfectly symmetrical flow field around it. Okay. But as we start increasing the Reynolds number, we will start having flow separation here at the back, and then nature would then cause that one of them would break away. And the moment it starts breaking away, the flow regime at the back would become very chaotic. Okay. And with the previous lecture, I've shown you a video. So let me just show it to you again. Okay. Typical video that you can get on YouTube. This one is going to be too slow. Let me rather get another one. Right, there's a better one, another one. Okay, there we can see the flow first symmetrical, and then it starts breaking away. So it's the same thing that you will hear when you're standing next to a power cable or a telephone cable and the wind is blowing. The sounds which is generated is because of the flow there at the back, and the result of that is also that the pressure distributions around the cylinder would not be symmetrical anymore. And if it's not symmetrical, it would mean that the forces, the pressure forces in terms of the lift, would then cause this thing to start oscillating. Okay, so we've seen it many times, and that is typically the reason why we get something like that. Now, you also know that one of the things that is being done for those of you playing golf is that on the outside surface, the geometry, you can put in dimples. Okay, and the result of that would be that transition would do something like that. So that is for a golf ball. So transition would be much earlier. All the dimples would actually make it more difficult for the flow to break away. And the result would be that the drag would actually decrease if we do that. Okay. Now that doesn't mean that for every body that you want to consider in industry you should make a rough. Okay. It is just that in the case of a golf ball, typically with the velocities that is being used, the result would be very favorable in terms of the drag coefficient, which can decrease, I think, almost with an order of magnitude. So this one is typically for a smooth tube, and that one would be for a rough one. Right, now if the drag looks like that, then you can be sure that the Nusselt number, if we look at the Nusselt number, also as a function of Reynolds number. We've seen it previously from the Colburn analogy, and that this nature tells us that the momentum and heat momentum, the forces in terms of momentum, Newton's law, and the energy equation actually are very similar. So typically, if you get these types of results with your drag, you'll get exactly the same with the Nusselt numbers. So the Nusselt numbers indeed would also do something like that, but what we can also do is we can look at the local Nusselt numbers before we get to the average ones. So the local ones would be typically be measured from a value of theta. Okay. So, sorry, let me rather change this to theta. The Nusselt number is a function of theta. Okay. Then the results would typically look at something like this. This is typically 80 degrees. Okay. And then we would get something like that. And this is typically as the Reynolds number increases from laminar flow to turbulent flow. So this is typically Reynolds numbers of 70,000, and that would be for 220,000. So the heat transfer, if you would heat this, and this flow around it, and you would measure the heat transfer at different points, then it would differ. Okay. Obviously, if we look at the Nusselt number as a function of Reynolds number, where previously this was local and this is average, okay, local values and average values, then the Nusselt numbers in terms of average values would typically also have a behavior very similar to that. Okay, now in your textbook are given equations that you can use to calculate the Nusselt number for a cylinder. Okay. So the Nusselt number for a cylinder is firstly given by the equation of Churchill and Bernstein. Equation 735. It's a little bit of a long equation. I'm not going to write it down now. I'm going to do it later when we do a problem. Okay. So that is equation 735 of Churchill and Bernstein. This one is for a cylinder, and then there's another one of Whittaker, which is for a sphere. Okay. Equation for a cylinder, an equation for a sphere. Okay. Now you'll see that these equations are relatively long. Okay. And what many people did is they took these equations and they made them simpler and easier to use. And what they would do is, and we've spoke about this many times, is to write the Nusselt number as a constant multiplied by the Reynolds number to the m to the Prandtl to the n. And they would do it for different geometries. Okay. So they would do it for different geometries, and for the different geometries, those three values would typically change. Well, this one normally would always be approximately a third. So in your textbook, take a look at table 7.1. I'm going to show that to you quickly. Okay, there you go. Please take a look at it. Table 7.1. Okay. Ladies and gentlemen. Okay. Okay, take a good look at it. So on the left, you'll see all the different types of geometries. There's a circle, a square, vertical plate, an ellipse. 7 different types of geometries. As I've said with the beginning of the lecture, there are actually many, many more available in literature. But these 7, some of the most important ones. Then they would give us, if it is the information, if it is valid for a gas or a liquid. Okay, then it gives us the range of the Reynolds number. And then lastly, an equation that we can use, which is of this format. The Nusselt number is equal to a constant multiplied by a Reynolds to the Prandtl to the third. Typically, look at all the Prandtl numbers. What do you see? They are all a third. Okay. What differs is the constant and the Reynolds number exponent. Those are the only 2 things that differ. You agree? Okay. Let's do an example. The example is based on example 7.5 in the textbook of Sengel and Gijar. Okay. And it is a steam pipe. Okay. A steam pipe with a length of 10 meters and a diameter of 150 millimeters. A diameter of 150 millimeters, and you're working there at Eskom, okay, and it's winter, and there's a wind blowing 10 meters per second, and the temperature of the wind is 0 degrees Celsius, and it so happens that the piece of the insulation on the tube is not there anymore, and the temperature of the pipe is 150 degrees Celsius. The question is determine the heat transfer rate. Okay. So we've got a pipe, 10 meters in length, diameter 150 millimeters, 6 inches, crosswind 10 meters per second, the wind temperature 0 degrees Celsius, and the surface temperature of the pipe is 150 degrees Celsius. The question is, determine the heat transfer rate from the pipe. Okay. Now, we need the properties of air, and we need to get the properties of air at the film temperature. Okay, ladies and gentlemen, can you please quiet down, please? Okay, so we need the properties of air at the film temperature. How do we get the film temperature? We get the film temperature by using the surface temperature and the free stream temperature divided by 2. So that would be 150 plus 0 divided by 2. It means we need to get the properties of air at 75 degrees Celsius. Okay. Please look in your textbook for me for the properties of air at 75 degrees Celsius. And to save you time, look at table A15. Okay, table A15. Okay, so this power station is here on the eastern side of Pretoria, okay, where you're working. And that is the conditions. So please quickly give me the properties of air at 75 degrees Celsius. Okay, so as you see, unfortunately, the properties are given for 70 degrees Celsius and 80 degrees Celsius, and you need to do interpolation. Do you agree? All happy with that? Okay. There's just one catch. Okay, and the catch is in a fine print at the bottom, and that has to do with the pressure. Okay. I've said it's here on the eastern side of Pretoria, and we know typically the atmospheric pressure would then be about 80 kilopascals. It wouldn't be 101.325 as in sea level. So these values are given in the textbook for 1 atmosphere. 1 atmosphere is 100 kPa. Okay, 100 kPa. Okay, so let's do it for 100 kPa. And what we're then going to do afterwards is we are going to make the adjustment. They tell us how we should do the adjustment at the bottom of the table. Okay, and then we're going to do the adjustment for a pressure of 80 kilopascals. Okay, now the properties is the following. The thermal conductivity is equal to 0.02917 watts per meter Kelvin. The kinematic viscosity is equal to 2.073 multiplied by 10 to the minus 5 meters squared per second. Prandtl number is equal to 0.7167. Okay. And remember, this kinematic viscosity is the viscosity divided by the density. Okay, are you all with me? Okay, so we've got all the properties now. Let's determine the Reynolds number. The Reynolds number we can write as rho Vd divided by the viscosity, or we can say it is equal to the velocity multiplied by the diameter divided by the kinematic viscosity. So working with the kinematic viscosity or the other one, it is your choice. You can use which one you want. Okay. Right, now if we go and calculate the Reynolds number, the velocity is 10 meters per second. The diameter of the tube or the pipe is 150 millimeters divided by the kinematic viscosity, which is equal to 2.073 multiplied by 10 to the minus 5. And the result is a Reynolds number of 72,373. Reynolds number 72,373. Reynolds number is equal to the velocity multiplied by the diameter divided by the kinematic viscosity. Velocity is 10, the diameter is 150 mils. The kinematic viscosity from the table, we can calculate the Reynolds number. Right, now that we have the Reynolds number, we have two options. If you look at the information available in the textbook, I've said that there's an equation for a cylinder, the equation of Churchill, and there's tables. So what I'm going to do is I'm going to use both approaches. Now, the equation of Churchill and Bernstein, okay, which is equation 735 in your textbook. Okay. This equation looks like this. It says the Nusselt number is equal to 0.3 plus 0.62 multiplied by Reynolds to the half multiplied by Prandtl to the third divided by 1 plus 0.4 divided by the Prandtl, everything to the 2/3, and then all that to a quarter multiplied by 1 plus the Reynolds number divided by 282,000 to the power of 5/8, and then close the brackets to the power of 4/5. So that is the equation of Churchill and Bernstein, and you'll understand now why I didn't want to write it down previously. Okay, so a little bit of a long equation. A little bit of an irritation if you quickly want to do it on your calculator, but if you're a little bit more patient and you can do some programming on your laptop or you do it in Excel, it's very simple. It's no problem solving this equation. Okay. Okay. Now, I'm not going to put in all the values because we have it. Okay. The Reynolds number is that. Okay. Prandtl number is that value there. Okay. Go through everything. Everything is Reynolds and Prandtl number. Okay. And to save time, it is equal to 174.6. Okay. And the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity, which then would be equal to 174.6. So that is the Nusselt number. Okay. And the result is we can get the heat transfer coefficient because we've got the diameter, 150 moles. Thermal conductivity is 0.02917, and the result is that we can get the heat transfer coefficient as 33.94 watts per square meter degree Celsius. Okay. And then we can calculate the heat transfer as the heat transfer coefficient multiplied by the surface area multiplied by the surface of the tube minus the wind temperature. Okay. The surface area would be equal to pi multiplied by the diameter multiplied by L. It's just the outside area of the 10-meter long tube. So it is pi multiplied by 0.15 multiplied by 10. We've got the heat transfer coefficient, the surface temperature is 150, the wind temperature is 0, and the result is, if we calculate it, that the heat transfer rate would be 24 kilowatts. Okay, so 24 kilowatts of heat transfer in 10 millimeter tube. Right. That's the one approach. Let's take the lazy approach. Okay. Alternative is to make use of table 7.1. And Aaron, if you can just zoom in there on the table for us. So if you look at the table, I'm going to give you a minute. Okay. What do we have to do? Okay. Firstly, we see the first geometry is the circle, so that's fine. That's the one that we are looking for. It's valid for a gas or a liquid, so air is a gas, so it's valid. And now we have to choose the Reynolds number range. The Reynolds number was given as 72,000, so 72,000 would give us the last equation. You agree? Okay. So that equation that we've then selected is equal to 0.027 multiplied by Reynolds to the 0.0805 multiplied by Prandtl to the third. Okay. Again, it's very elementary. We have the Reynolds number, we have the Prandtl number, so you just have to do the calculations. And if you do it, then the Nusselt number would be equal to 197.2. Okay. So if we compare it to previously, we had 174. So we can see there is a difference. Okay. And then from that, we can calculate the heat transfer coefficient. Of course, the Nusselt number is then equal to 197.2. We do have the diameter, we have the thermal conductivity, and the result is that we can calculate the heat transfer coefficient as 38.34 watts per square meter degree Celsius. Right, and now we can calculate the heat transfer rate with this approach, and that would then be equal to the heat transfer coefficient, again multiplied by the area, surface temperature minus the wind temperature, and the result is 27 kilowatts. Okay, so 24 kilowatts, 27 kilowatts, sure, it is not the same. It's approximately the same. And as always, listen very well, as always, the selection of the equations to be used will always depend on your situation. Okay, if you're on the plant and you're just looking at energy savings potentials, okay, and you'd like to look at typically how much you can save, then an order of magnitude type of calculation would be fine. If you want to do detailed design, where you're designing something where you want to compete against other people with products, then obviously you need to go and get more accurate equations. Also in the fine print, in many cases you will see that many of these equations, even the long ones, can have an uncertainty of plus or minus 30%. It's not unusual. So there are not a lot of data in convection heat transfer with uncertainties of plus or minus 10%. It's very, very unusual. Question?
It's not the air is flowing over the pipe from that direction. Now, what if you sent the air through the pipe? Would the Reynolds number still be the same? And like, when you make it, are you supposed to use a projected area when you calculate some of the values, like Q or whatever?
Okay. Okay. The question is in terms of what about the Reynolds? What about the flow inside the tube?
Say the wind wasn't in that direction; it was through the pipe. Then the Reynolds number still be the same. Is it irrespective of the direction of the
airflow? So his question is, I mean, if we have airflow over the pipe, okay, in comparison maybe with airflow from this direction that goes through the pipe, will we calculate the Reynolds number the same? The answer is, it depends on the person who developed the equation or did the experiments, okay? So in this case, if you go and look at the table, okay, and the equations, the Reynolds number is specifically based on the diameter. Okay. Some people might have said, well, I would actually like for my external flow to base it on the length. You can also do that, but then the equations would look differently. Okay. So if you have flow 10 meters per second through the tube, then as far as I know, there are not even one equation that I know of that if they would then calculate the Reynolds number, would not use the internal diameter. So yes, so in this case, the Reynolds number would be the same for external flow and internal flow. Okay. The internal flow we're going to do in the next chapter. Where things becomes a little bit more complicated is, in many tubes on the inside, we have fins. Okay, like that, which are being used for enhanced heat transfer. And in some cases, or in many cases, these fins are also spiraled, okay, like in a barrel of a rifle. Okay, so they are spiraled on the inside. So the idea, of course, is to rotate the flow on the inside. So if you now have to calculate the Reynolds number, then the question is, do you do it with this diameter? Do you do it with that one, or do you use the average? Again, there are different equations which were developed by different people. Some of them use this diameter, some that, and some the average. It depends on the developer.
The heat flow, that 24 kilowatts,
right.
For the area, do you use, I see you use the area on the cylinder. Aren't you supposed to use the projected area in the direction of the airflow?
No, because if we have a tube like this, ladies and gentlemen, okay, so his question is, if we have the airflow in this direction, okay, which means that this air would see something like that. That is the projected area, okay? Okay. Now, the heat transfer is not only from this part of the cylinder, okay? The heat transfer is on the back also. So this Nusselt number that that has been calculated here is the average around the cylinder. If we come back to, ladies and gentlemen, okay, the local values. Okay, if you would have used the local equations, okay, these ones, then it would have been possible for you to maybe break it up in segments, and then for the different segments get the Nusselt number, and for that one then calculate the heat transfer. So if you in the lab would do these types of experiments and you would prefer to use this area, you could have done it. It's fine, as long as you've defined it very clearly for other people to use. Okay. Normally, just not like that. Okay, any more questions? Yes?
I would like to find out what happens to, in the situation that the airflow changes to an arbitrary angle other than the
Yes. Okay, very good question. What happens if this angle would change? Okay, if the angle would change, you need another set of equations. Okay.
Because I do notice that the,
Yep.
that the equation is used for an ellipse, which basically becomes ellipse with closed angle, and the circles are quite different.
Yes. Yeah. Okay. So the question is, I mean, if the wind direction would change, what happens then? The answer is we need to get other equations. The equations in the textbook is a small selection of what is available in the literature. If they would have put everything in here, you know, the textbook would have been, it is just too much information. So an ellipse, for the ellipse, for example, ladies and gentlemen, yeah, we will see that things changes from the cylinder. If you can just zoom in again on the table, please, Erin. If we look at the cylinder, we will see that the Nusselt number is a function of Reynolds number, okay? Do you see it? While with the other geometries, we've got a range of Reynolds number, and then we have one equation, okay? So coming back to fluid mechanics, if you go back to fluid mechanics, if you have a geometry like that, and you would look at the flow around it, this flow is not as sensitive for if we start increasing the Reynolds number very, very slow, and we start increasing and increasing and increasing it, it doesn't have this type of transition where you suddenly have something like that. Where at the back, the flow, there are flow separations, and they start breaking away, and they're not symmetrical. They're always symmetrical, okay, for the Reynolds number range that they've given us. And if the body starts becoming more aerodynamic, like a sphere, okay, then the separation, if there is separation, would become smaller and smaller. So the results would become, let's call it, more stable than for something like a cylinder or a sphere. Okay. Right. Any more questions, ladies and gentlemen? Okay. The last part in the textbook is flow across tube banks. Okay, flow across tube banks.
If we suppose to account for the expression that's not at one.
Oh, yeah, sorry, yeah, thanks. Okay, I forgot, okay. One of the things I've asked you is the pressure. Okay, we've said the tables is valid for a pressure of 100 kPa. Okay. Now what happens, obviously these calculations would then be valid for power station at sea level. If it is here on the eastern side of Pretoria, typically where the pressure is 80 kPa. We need to adjust the values. Okay, we need to adjust the values. Okay, now what I did is I've adjusted it using ease because it is just more simple. And when I then calculate the K value, it was equal to 0.02917. I'm not going to write down the units to save time. The kinematic viscosity is equal to 2.591 multiplied by 10 to the minus 5. and the Prandtl number is 0.7167. Okay. Right, so if we compare this to the values at 100 kPa, we would see that there's a small change in the viscosity. You see? Small change in the viscosity. Okay. Now, if we use that small change in viscosity and we would do all the calculations again, then we would get a Reynolds number of 57,898. So the Reynolds number changes a little bit. And then, using the two different methods, firstly a Nusselt number of 151.4 for the first method, which is the equation, and then this one would be 164.8 with a table. Okay, so this is with the equations. Okay, and that is with the table. So we can see there's a little bit of a difference. And then the result would be for the first one 21 kilowatt, and for this one 22.7 kilowatt. Okay. So it does change a little bit. It is important to remember that the properties, and also if you get properties in a textbook or a table or whatever, make sure where it is valid. Okay, so in this case, it's valid for 100 kPa. Your application is now at 80 kilopascals. At the bottom, they tell you how you can adjust the values. And if you do that, you can see that there are small changes in the results. Okay. Yep, question?
So how would you go about changing those values? Because I think you use the two temperatures that will first you divide and
Okay, the question is, how do we change the values? Please just go for me to the table. Okay, listen. Okay, so what they say is, take note, for ideal gases, okay, for ideal gases, the properties of CPK and viscosity and Prandtl are independent of pressure, okay? But the properties of density, take note, the density, the kinematic viscosity, and alpha, we will get to alpha later, the thermodiffusivity, at the pressure in 1 atmosphere, other than 1 atmosphere, are determined by multiplying the values of the density at the given temperature by P and by dividing the kinematic viscosity and alpha by P. So it just means you use the ratio of 100 to 80. That ratio you use to make the adjustments for the values. Okay. So it's very simple. But take note, it has been generated for ideal gases. For ideal gases. Okay. Not for air. Okay. Ladies and gentlemen, let me just finish quickly. Okay. The last, I know you have to write test. Just keep that. Okay. The last part is the part on 7.4, and that is about tube banks. Okay. This is now a typical application where we've moved from the flat plate, very simple geometry, to a cylinder or a sphere, to something more practical. Tube banks are typically found in industry, in many applications, and there are two types of tube banks. The first one is called in-line. Okay, an in-line tube bank. So all the tubes are like that. And the second one is staggered. Okay, so staggered typically would look like that, with a flow direction like that. Okay, so that's a flow direction. And obviously that is the diameter. Okay. So different advantages and disadvantages of all of them. Typically these are being used especially in the air conditioning and refrigeration industry, where we have condensers and or evaporators, and in many cases there will also be fins involved in between. But let's first take out the fins and study that. Okay. So for those applications, again, the equations are given in the textbook. But there's just one thing that is very important there to remember, and that is that in this case now, the Reynolds number is calculated as rho multiplied by the maximum velocity multiplied by the diameter divided by the viscosity. Okay. The maximum velocity, not this velocity. That is the free stream velocity. Okay, the free stream velocity. The maximum velocity is very easy. It will be calculated there. Vmax. Okay. Okay. And it's very simple. All we do is we take this area minus the projected area to calculate the Vmax. When we have the Vmax, we have the Reynolds number, and then we have all the different types of tube banks. You can get all the equations or the Nusselt numbers and calculate the heat transfer rate from the tube bank. Okay. Any questions, ladies and gentlemen? If not, thank you very much.